We'll continue now with the other different types of carbohydrates. Now, we already learned about different monosaccharides, their properties, their isomerism that are possible. To go further, we go on now to the disaccharides. What are disaccharides? When two monosaccharides condense together, you get a disaccharide. The bond which is formed between the two monosaccharides is called as a glycosidic bond. The glycosidic bonds also have a nomenclature. They specify the anomer that is present in each of the monosaccharide and what type of bond, which carbon atoms are involved in it. So we'll have a look at the different disaccharides which are important biologically. Please have a look. The disaccharides, if you look at the different disaccharides, sucrose, where is it present? It is present in cane sugar, wheat sugar, table sugar, everywhere we have sucrose. It is made up of glucose and fructose, important for you from MCQ point of view, and the bond between them is alpha-1 beta-2 glycosidic bond. Does it have reducing property? No. So whenever the anomeric carbon atom is not free, then it becomes a non-reducing sugar. We have another disaccharide that is important, and that is lactose. Lactose is also called as the milk sugar. It is made up of galactose and glucose. The bond is beta-1,4 glycosidic bond, and it is a reducing sugar. Maltose is another disaccharide. It is malt sugar. It is made up of two molecules of alpha-D glucose, and the bond is alpha-1,4 glycosidic bond, and it is also a reducing sugar. So we go on to monosaccharides are over, disaccharides are over. There are a few oligosaccharides, as I said, like maltotriose, etc. But however, they are biologically produced during digestion or something like that. So other than that, more important are the polysaccharides. Which are the polysaccharides? Now, all polysaccharides can be classified as, the polysaccharides can be of two types. Which are they? If they contain the same type of repeating monosaccharide units, same type, we call them the homopolysaccharides. Homopolysaccharides. If the monosaccharide unit that is repeating is different types of monosaccharide units, then we call it a heteropolysaccharides. So two different types, homopolysaccharides and heteropolysaccharides. Now I'll give you some examples of homopolysaccharides. Let's have a look here. The homopolysaccharide starch, where is it present? It is present in plants. It is made up of only D-glucose molecules. Though we say that starch is made up of two components, amylose and amylopectin, all of that is made up of alpha-D glucose unit itself. Now, when these glucose units are attached to each other in a straight chain, if the glucose units are attached to each other in a straight chain without any branches, it is called as alpha-1,4 linkages. This is 1,4 linkages, it forms a straight chain. Then this straight chain usually forms a secondary structure which is somewhat like a helix. So this helical structure is called as amylose, whereas amylopectin is also present in starch. However, it has branches in it. Amylopectin has branches in it. The number of branches, where the branches occur, is also slightly different from other homopolysaccharides. So we have starch is made up of amylose and amylopectin. Amylose has a helical structure. Amylopectin has a branch structure and it does not form a helix. Now we come back to this. The other homopolysaccharide that is important is glycogen. Glycogen is present in animals, not in plants. So where in the animals it is present? It is present in the liver and the muscle. It is also made up of only glucose. It is a homopolysaccharide. So it is glucose, but it is highly branched. It has lot of branches in it. Compared to amylopectin, it is much more branched, but somewhat similar to the structure of amylopectin, but more branches. Dextrins are also an important polysaccharide, homopolysaccharide. They are got by the partial hydrolysis of starch. Again, they are made up of D-glucose. Cellulose. Cellulose is another important homopolysaccharide. It is present in the walls of plant cells like cotton, wood, etc. It is made up of beta-D-glucose. As I said, beta is a anomeric form, alpha is another anomeric form. But what is important here, look at it, just because the position of OH has changed, it has a different anomer of glucose, it is not digested in the body. Our body does not have the enzymes to digest beta-D-glucose. But is it important? Yes, it is the cellulose which contributes to the dietary fiber. Another important homopolysaccharide is inulin. Another important homopolysaccharide is inulin. It is present in bulbs like onion, garlic, etc. It is made up of exclusively D-fructose. It is used to find the glomerular filtration rate or the renal function test, different renal function tests. Another important homopolysaccharide is inulin. It is present in bulbs like onion, garlic, and it is made up exclusively of D-fructose. It is used to find the glomerular filtration rate and also as a part of the renal function test. Another important homopolysaccharide is the dextrans. The dextrans are produced by bacteria. It is also made up of only D-glucose. It is highly branched and it is used as a plasma expander, especially in cases of shock. So here we have got three terminologies. But what is the difference? For example, dextrose is glucose, dextrin is formed because of partial hydrolysis of starch, and dextrans are got from bacteria, they are the plasma expanders. Let us not get confused between dextrose, dextrins and dextrans. The spelling becomes important here. Now we go on to the heteropolysaccharides. The homopolysaccharides and the different examples are over, out of which starch and glycogen are important. We go on to the heteropolysaccharides. Heteropolysaccharides, what does the name mean? It means that they are supposed to have different types of monosaccharide units. Now, one of the most important one is agar. Agar is made from seaweeds. It contains galactose, glucose and other sugars and used as a support medium in immunodiffusion, immunoelectrophoresis, culture media. Everywhere agar is used. Now, other than that, biologically important, which the heteropolysaccharides that are present within the body are important. I am going to talk more in detail about this. They are called as the glycosaminoglycans. Glycosaminoglycans, please look here. In this slide, as I have told, they are the mucopolysaccharides. Why do I call them mucopolysaccharides? They are the large complexes of negatively charged heteropolysaccharides. They are attached to a protein and the compound is called as Proteoglycan. In a Proteoglycan, nearly 95% is carbohydrate and 5% is protein. I'll be talking more about Proteoglycans and how they are formed. Heteropolysaccharides or the mucopolysaccharides, glycosaminoglycans, are not used to give energy because they are the structural polysaccharides. They form the structure of the human body. In this, they are important. But because of the presence of various charged groups, because they have a lot of negative charges, they attract water, produce viscous solutions and form a gel-like matrix, and that is where mucopolysaccharides are important. Now I'll go on to a bit more about the structure of the glycosaminoglycans. They are long and unbranched. They are formed of repeating monosaccharide units. Though I've shown it as a straight line, they are more like this. These heteropolysaccharides are made up of repeating disaccharide unit. The disaccharide unit can be an uronic acid with another compound. This, I'll talk in detail of the different heteropolysaccharides, the composition of the different heteropolysaccharides. I'll be talking in detail. All of them are made up of uronic acid or another amino sugar. That is why the name glycosaminoglycans, because they have an amino group. That's why the name glycosaminoglycans. This disaccharide unit is repeated many times. Disaccharide unit is repeated many times. They form long and unbranched. Because of the presence of this acidic group, because of the presence this amino group is also acetylated, most of this will have a lot of negative charges. And because of this negative charge, they have different properties that are possible. So as I said, a disaccharide unit is formed of a uronic acid and an amino sugar. So we can represent it as like this: uronic sugar, amino sugar. Amino sugar means a sugar with an amino group. Uronic acid, where the carboxyl group is converted into an acid, uronic sugar. Many times this amine group is also acetylated, giving it the negative charge. Now because of the large negative charges, it is repel each other. So that is why extended chains are formed. And when they have so much of negative charges, they will all be surrounded by a shell of water. The shell of water will surround the whole of this chain. And this is the most important property of glycosaminoglycans. When it is surrounded like this, it gives it a slippery feeling. It is as though, imagine two magnets which have got the same poles are closing towards each other. They will slip over each other. Similarly, these glycosaminoglycans will slip over each other. They have something repelling them from coming together. And that is why not only they form a straight chain, they slip. And this type of resilience is very important for different movements that are possible. And that is where these glycosaminoglycans are distributed in the body. Now, I'll talk about the different glycosaminoglycans. The first one that is important is hyaluronic acid. Now, the disaccharide unit is glucuronic acid and N-acetyl glucosamine. I have made a table for this. I'll show all of them together. Glucuronic acid and N-acetyl glucosamine. What is the importance of hyaluronic acid? It is present in loose connective tissue, synovial fluid, vitreous, humor of the eye, umbilical cord and cartilage. It serves as a shock absorber and a lubricant. Again, it is because of its negative charges. It is unsulfated and it is not covalently attached to any protein. That is its most important feature. It is also found in bacteria. Now, an important enzyme is hyaluronidase enzyme, and this is secreted by the invasive bacteria and helps in the spread of bacteria through the subcutaneous tissue, and it is also present in sperm and helps in the fertilization and formation of the zygote. Now, the next important heteropolysaccharide is chondroitin sulfate. It is also made up of D-glucuronic acid and N-acetyl galactosamine, which has been sulfated, found in cartilages, tendons, bones, ligaments, aorta, etc. Now, the third is heparin. Heparin is sulfated glucuronic acid and sulfated glucosamine. I have just shown you the sulfur groups. Heparin is an anticoagulant. It is present within the cells and is present in the mast cells, present in the endothelial cells of the blood capillaries, present in lung, liver, kidney, spleen, etc. Or in all these places, heparin is present. Heparan sulfate is one more heteropolysaccharide. In this, it is acetylated. Compared to heparin, it is acetylated. That's the only difference, and maybe a bit lesser of sulfur groups, and it is extracellular, found in basement membranes and cell surfaces. Dermatan sulfate is made up of iduronic acid and N-acetyl galactosamine, found in skin, blood vessels and heart valves. So, Keratin sulfate is galactose and N-acetyl glucosamine. It is the only glycosaminoglycans which does not contain uronic acid, and that is important in MCQs. The heteropolysaccharide which does not contain uronic acid is Keratin sulfate. There are two types. One is found in cornea. Keratin sulfate 2 is found in loose connective tissues. So here is a summary table which tells you the different structure. Hyaluronic acid is made up of glucuronic acid and N-acetyl glucosamine, N-acetyl glucosamine and glucuronic acid, present in synovial fluid and vitreous humor. Chondroitin sulfate, present in cartilage, tendon and ligaments, is made up of glucuronic acid again, but sulfated N-acetyl galactosamine. Heparin is present in mast cell, liver, lungs, etc. is glucuronic acid, sulfated N-glucosamine, sulfated glucosamine. Heparan sulfate is present in basement membrane, It is made up of sulfated glucuronic acid and sulfated glucosamine. Dermatan sulfate is present in skin, made up of iduronic acid and N-acetyl galactosamine. So keratin sulfate present in cornea, loose connective tissues, made up of galactose and sulfated N-acetyl glucosamine. So if you look at this structure, the table, if you look at the structure, which is very difficult for anybody to remember, which is made up of what, I would suggest the main thing that is to be remembered is the keratin sulfate is the only glycosaminoglycan which is not made up of uronic acid. All others have sulfated compounds in it except hyaluronic acid, and if you look at it, glucuronic acid is present in hyaluronic acid, chondroitin sulfate, heparin everywhere, and heparin sulfate all contain glucuronic acid. Dermatan sulfate is the only glycosaminoglycan which contains iduronic acid. That's the thing that is to be remembered out of it. So we go on to what is this, what will happen to this, how are they formed, how are they this, and that is known as proteoglycans. Now all the glycosaminoglycans are attached covalently to proteins, all except hyaluronic acid. Only hyaluronic acid is free in nature. Now when they are attached to a protein, I am going to draw this protein like this. This is a protein is called as the core protein, and these, as I said, they form extended rings. These are attached to the core protein. So what does this structure look like? What is this structure? It is called as the bottle brush appearance. This is because this core protein is this is a core protein, and this is how the glycosaminoglycans are attached to the core protein. This is a proteoglycan monomer. Not only this monomer is just like that, they are further attached to another compound. Such type of monomers are present in attached to, what is this compound here? This is hyaluronic acid. Hyaluronic acid contains these proteoglycan monomers attached to it. One more, different places, a core proteoglycan with its glycosaminoglycans. Core protein with its glycosaminoglycans. So this much gives it, the proteoglycans, a good firm structure, and that is what is present in different places. Now I want you to look at this bottle brush appearance. All glycosaminoglycans are found covalently attached to proteins, gives it a bottle brush appearance. The core protein with the glycosaminoglycans chains are extending out. The linkage is through a trihexoside, galactose, and xylose, and to serine of the core protein. There are different names for these proteoglycans. Example, Syndican is a membrane proteoglycan. Versican, Agrican are extracellular proteoglycans. Neurocan, Cerebrocan are present in nervous tissue. Proteoglycan. These proteoglycan monomers are aggregated by associating with hyaluronic acid. Not only are they present over here, they also have link proteins which connect the core proteins to the hyaluronic acid. So link proteins are also involved over here, and it stabilizes the proteoglycan aggregates. So that is proteoglycan, everything about glycosaminoglycans, the core protein, their aggregate forming a proteoglycan. This is proteoglycan has got 95% of glycosaminoglycan, only 5% protein. Rest of it is glycosaminoglycan. Now, what are these chains? Can these glycosaminoglycans be different? Yes, it could be a combination of chondroitin, combination of dermatan sulfate, chondroitin sulfate, everything except hyaluronic acid. Hyaluronic acid is present here. It is to that which the core proteins are attached. That is the thing to be taken home. Now we go on. After proteoglycans, what are glycoproteins? I think this is something which you all know about. Whenever a protein is having a carbohydrate chain, we call it a glycoprotein. When the carbohydrate content is less than 10%, we call it a glycoprotein. Remember, in proteoglycan, the carbohydrate content is 95%, whereas in a glycoprotein, the carbohydrate content is only 10%. So most of the secretory proteins are combined with the carbohydrate part. You look at enzymes, they are glycoproteins. You look at transport proteins, they are glycoproteins. You look at hormones, they are glycoproteins. So many hormones, you have transporters, transport proteins, structural proteins. Many of these are glycoproteins in nature. So the different carbohydrates that can be present in glycoproteins include mannose, galactose, N-acetylglucosamine, N-acetylgalactosamine, NA, xylose, etc. So here are certain examples of glycoproteins. Mucin and mucus secretions contain a lot of glycoproteins. The blood group substances and the histocompatibility antigens are also made up of glycoproteins. Some hormones as luteinizing hormone, thyroid stimulating hormone, follicle stimulating hormone, etc. are glycoproteins. Some enzymes and clotting factors are glycoproteins. Immunoglobulins are glycoproteins. So that completes the chemistry of carbohydrates. To summarize, I would like to say all carbohydrates can be classified into monosaccharides, disaccharides, oligosaccharides and polysaccharides. Monosaccharides have a single unit of saccharide, include the trioses, tetroses, which can be again classified into aldoses and ketoses. Depending upon the functional group, monosaccharides exhibit isomerism, D and L form anomerism, alpha and beta forms, and they also exhibit optical activity. Optical isomers are also possible. Monosaccharides have certain properties like they can form alcohols, they can form reducing properties. They have amide sugars present in mucopolysaccharides. We go on to the disaccharides. Disaccharides, most important are sucrose, lactose and maltose, present in different places. I've told you sucrose is made up of glucose and fructose, lactose is made up of glucose and galactose, maltose is made up of glucose and glucose. So this is the main disaccharides that are important. Coming to the polysaccharides, it may be heteropolysaccharide or homopolysaccharide. Homopolysaccharide include compounds like starch, inulin, glycogen, cellulose, etc. depending upon the different composition. If you go to the heteropolysaccharides, we have different types like hyaluronic acid, chondroitin sulfate, keratin sulfate, dermatan sulfate. All these glycosaminoglycans are all interlinked to form proteoglycans. So that is heteropolysaccharide. And we can also have glycoproteins. That is, when the carbohydrate is attached to a protein molecule, you call it a glycoprotein. So that completes the chemistry of carbohydrates. In my next class, I'll be talking more about chemistry of proteins. Thank you.